Bismillah ar-Rahman ar-Rahim. Today we have very interesting theorem in calculus called the fundamental theorem of calculus. You know, we have two interesting problems in calculus. The first one is called the tangent problem. That is the problem of finding the slope of the tangent line at a specific point for a certain curve. That leads to what we call differential calculus. The second interesting problem is the area problem. How to find the area under the curve between A and B. Okay. Now these two problems seems to have no relationship, but actually it is found later that these two problems are closely related. What is the fundamental theorem of calculus? We have two parts of the theorem. We will discuss this theorem in details in this talk. Okay. To get an idea about the fundamental theorem of calculus, what do we have here today? We will define, so we consider the following function. We consider the following function, which is g of x, a function of x. Okay, we are familiar with some functions like, for example, here we know what is the meaning of x squared, we know what is the meaning of sine of x, we know what is the meaning of exponential of x, and so on. We know what is the meaning of each of these functions. Today, we will introduce a new type of functions. That is a function defined in terms of integral, a to x. If we have a function f of t, now what we need to do, we define a function called g of x that is defined in terms of integral. Just to get an idea, what does it mean? Let us see it geometrically here. For example, if we have, now this is t and this is f of t, so we have a function here called f of t. This is what we have. Taking a special case where the function is greater than or equal to 0 all the time, then we are specifying a certain point here called a, and we are trying to define a function in terms of the integral. Now, from the previous discussion we made, if you specify a certain point here, x, and then you integrate from a to x, f of t dt, that will give us what? The area under the curve. Okay, if you change x, this will give you a different number. So this is a new type of function. What you need to do, we need to study what is the derivative of this function. Okay, what is the derivative of functions defined in terms of integrals? Then we will study the relationship between the two problems, the tangent problem and the area problem, or the differential operator and the integral operator. Okay, so that will be done in the next paragraph. Before I go and explain the fundamental theorem of calculus, I will do some small exercise that will explain the idea. So what do we have here? I will just recall this because this is something we did from the definition of integral. We have done something like this from a to b, and we have here t squared dt. This is equal to what? This will be equal to b cubed minus a cubed over 3. That can be shown by the definition of integral. Now, what is the experiment I need to do? I need to convince myself that this is well-defined function, so I will take a specific exercise to see how to calculate these functions at a certain point. So what I will do here as a small exercise, I will specify our f of t here to be just t squared, okay? This is our function here. And I will fix a to be equal to 0. I will fix a to be equal to 0. And I need to ask myself the following question. What is, this is part A, let us say, what is the value of the function here at 0? What is g of 0? What is g of 1, for example? Let us find more. What is g of 2? What is g of x here? G of x, as before, is defined to be equal to, in this specific case, I'm defining g of x to be from a to x f of t dt. I'm choosing now a specific f of t, which is t squared. I'm choosing a to be specific to be 0. So I'm considering the integral from 0 to x, what? T squared dt. I'm trying to make myself familiar with evaluating these type of functions. So what does it mean, g of 0? Now, g of 0, just you need to replace x by 0. So you end up with the integral from 0 to 0. That is t squared dt. And clearly, this is equal to what? This is equal to 0 by the properties of integrals we did. If you integrate from 0 to 0, that will give you 0. So that is the evaluation of the new function we define, which is called g of x at 0. Okay, what is g of 1, for example, here? G of 1 is simply the integral from, according to the definition, it is 0 to 1. I'm replacing x by 1. And that is t squared dt. And using the formula I wrote there, which is a formula that can be derived from the definition of integral, this will give me 1 over 3. Okay? Because here we have a equal to 0 and b equal to 1. So that will give me 1 cubed minus 0 cubed over 3. That is 1 over 3. So the value of this new function at 1 is 1 over 3. Okay, we'll explain what is the meaning of this geometrically later. Let us find one more, which is g of 2. What is g of 2, for example? It is the integral from 0 to 2 t squared dt. And clearly by using the formula we have here, that will give 8. That will give 8 over 3. Okay, so it seems, yes, we have a well-defined function. If you specify a certain number for x, we get a specific value for the value of the function at that point. Now, let us try to find g of x. Let us find an expression for g of x for this specific exercise. What is g of x equal to? Okay, what is g of x? If we use the same formula here we get what? We get x cubed over 3. Why? Because we are integrating from 0 to x t squared. I'm using the formula here, so I'll get x cubed minus 0 cubed over 3. That is x cubed over 3. The question is, now, what is the following? What is the derivative of this function? D by dx of the function we are defining from 0 to x t squared dt. Okay? This is what we are trying to find here. But 0 to x t squared dt is just x cubed over 3. So this implies now g prime of x is equal to what? It's equal to x squared. Now, going back to the original function here, g of x equal to a to x f of t dt. A very interesting question is, what is g prime in general? What is g prime of x, where we have our g of x is defined to be the integral from a to x f of t dt. Of course, we are assuming that this function is continuous here. So the question, what is the derivative of this function? What is the derivative of this function? Before I go to explain this, I will just say some words about the meaning of the function here geometrically for that specific exercise. We have the y-axis here, something like this, and this is the t-axis or x-axis. I have y equal to f of t is equal to t squared. So t squared is just a parabola here. I'm just fixing this to be like this. This is f of t, which is t squared. And then I'm fixing the point a to b 0. What does it mean? G of 0, the area here, which is only 1 point, so that is 0. If I say g of 1, it means I'm calculating the integral from 0 to 1 for this specific exercise because it is non-negative. Then I'm talking g of 1 will give me this area here, and so on. G of 2, you need to come here, and this is 2. So the whole thing here is g of 2. In general, if the function f of t is sometimes positive, sometimes negative, this new type of function represent the net area. And our interesting question now, as a first part of that theorem, what is the derivative of this in general? What is the derivative of this in general? Okay, I will motivate first the conclusion, then I will write it as a theorem, which is fundamental theorem of calculus part 1. I will try to think about the derivative from the geometry first. Roughly speaking, it's not a precise one, but it is motivation for the definition, or it is a motivation for the conclusion we will have in the theorem. Again, let us look at it from the geometry here. We have f of t, something like this. This is y equal to f of t. Assume this is t and this is f of t, okay? Y equal to f of t. Now, if I specified a to be somewhere here at the beginning here, okay? What is the meaning of the derivative of this function? what is the meaning of the derivative? What is the definition of derivative function? If someone said, what is g prime of x? By definition, it is the limit as h goes to 0, right? F or g of x plus h minus g of x divided by h. So I need to think about this quantity. What is it in terms of this new type of functions? Okay, so I will try to see this quantity here. What does it mean for this specific choice of f of t, which is a function that is non-negative all the time, just to see an idea about the conclusion of this question. Okay, let us look at that. So I need to calculate something here. I need g of, let us say this is, for example, here, this is x. I'm choosing here, for example, g, or this is x plus h. Okay, this is x plus h, something like this. So according to our discussion now, we said this portion here will represent what? The integral from a to x, that will give me g of x. And from here to here, that will give me g of x plus h. So if I subtract g of x plus h minus g of x, what I will get? Actually, I will get exactly this portion of the graph. Look here. From here to here, this is g of x. From here to here, this is g of x plus h. If we subtract, we will get this part of the graph here. This is g of x plus h minus g of x. Okay, we'll try to find the area here. We will approximate this area. Because I have 2 points here, I can, this is h, of course, because the difference between them is h. But the height here, I can take it to be the left point approximation. I can take it to be the right point approximation. If I choose this one to approximate, then I will get here what? I will get f of x multiplied by the width here, which is equal to h. Fine. It doesn't matter. If we take f of x plus h, it doesn't make a difference here also. If I divide by h here, what do we get? I will get g of x plus h minus g of x all over h is approximately equal to f of x. Okay, I wrote approximately because here I'm choosing the left point approximation. But if I let h goes to 0, so these 2 points will be close to each other, what will happen here? I will have the limit as h goes to 0, g of x plus h minus g of x divided by h is equal to f of x. But what is this? This is exactly the definition of the derivative of x. As I said, this is not a proof, but this is just an idea about the conclusion. So, what is g prime, or this is g of x? According to what we have done here, it seems that the derivative of the function here, g prime of x, will be nothing but f of x. And this is exactly the conclusion of what we call fundamental theorem of calculus part 1. Of course, we need to add some conditions to ensure the existence of the integral. And that will be done in the first part of fundamental theorem of calculus. I will summarize now the conclusion of this discussion as a first part of fundamental theorem of calculus. Now, after this discussion, what is the fundamental theorem of calculus part 1? The fundamental theorem of calculus part 1 says if you have a function f that is continuous on the closed interval ab. So we need continuity over the closed interval. That means it is continuous in between and it is continuous from the left at b and continuous to the right of a. Then this new type of functions which we define g of x equal to a to the x f of t dt is also continuous. Not only continuous, it is continuous over the closed interval. It is more than this. It is differentiable on the open interval AB. And this is the formula that will give you the derivative of that function. Okay? So in general, what is the derivative of such a function here? The derivative g prime of x will be simply f of x. F of x. That is the summary of what we call fundamental theorem of calculus part 1. Now let us use it in some exercises. For example, here, the question say, find the derivative dy by dx for these specific functions. Okay, I need to remember the shape of the function I have. It has a constant downstairs here and a variable here, x. And this is f of t dt. It is not important here, f of t dt, f of u du, f of w dw. We commented this last time and we said this is a demi-variable, okay? So, what is the derivative here? What is y prime? What is dy by dx? Okay, we have here a function called t cubed plus 1, and we are integrating from 1 to x. Our target to differentiate over the integral sign. That is what we try to find, d by dx of the integral from 1 to x, t cubed plus 1. Now the fundamental theorem of calculus part 1 will help us to find the answer. It says simply what you need to do is just to replace t by x, so you get x cubed plus 1. Okay, so you are recovering the integrand in other words. Okay, the derivative from 1 to x of the integral from 1 to x, sure, t cubed plus 1 dt is x cubed plus 1. So it is direct application for the theorem. The second exercise says how to differentiate the integral from x to 5. Of course, this is a function of x, but it is not in the form we have here. We have from a to x f of t dt. But this is x to a, x to 5, 3t sine t dt. So what should we do? We need to use the properties of integrals we discussed before in order to rewrite it first in terms of the shape of the function we are discussing. Then we apply what we call fundamental theorem of calculus. So what should we do first? I will rewrite y as a minus sign integral from 5 to x. I'm switching the boundary point, so I need a minus sign here. This is 3t sine of t dt. Now we have it in the form of the fundamental theorem of calculus. So what is the derivative here? Y prime. What is dy by dx? In other words, this is equal to, of course, a minus is a constant, so we can take it out and then differentiate this. Okay? So what is the derivative of this function now? It is minus times all of this times 3x sine x. So what I need to do now, I just apply the fundamental theorem of calculus that says you just replace t by x. That's exactly what we did here. We replaced t by x, we replaced t by x. The minus sign came from the properties of integrals. That is the basic form of the fundamental theorem of calculus, the fundamental theorem of calculus part 1. Now we will just make a connection between what we have done here and the chain rule somehow. What I will do in the next example, I will change this x into a function of x. So let us do it in general. What is the derivative? This is the question. What is the derivative of an integral function or a function defined in terms of integral? If we have here, let us say a, and here we have g of x, not x, g of x, and inside we have f of t dt. Again, we are assuming here the function f to be continuous. Everything is fine. All conditions of the fundamental theorem of calculus is there. We are looking for the derivative of such a type of function. So what should we do? This is not exactly the form of the function we defined from a to x. We are changing x now into a function of x. So what should we do? We apply, if you remember, we did something like this in calculus 1 that says if we have f and we have here g of x, okay, we have some differentiability conditions here, everything is fine, f is differentiable and g is differentiable, etc. Then we have the chain rule that says the derivative of y is like f prime at g of x multiplied by g prime of x. It's like we are making this is equal to u. So we have y is a function of u and u is a function of x. So in another form of this, we can let u equal to g of x, and we say dy by dx is equal to dy by du times du by dx. So exactly what I will do here is the same argument we did before. So in order to evaluate the derivative here, what I will let here, I will let u equal to g of x. Okay? So what will happen here, if you allow me, I will call this function, all of it, I will call it y. Y is equal to the integral from a to g of x, and that is f of t dt, assuming the function here f is continuous. Okay, fine. What we are trying to do, we are trying to find dy by dx. That's the question here. So what is dy by dx? What is dy by dx? It is actually dy by du times du by dx, right? What we did here, we are replacing g of x by u. So what do we get here? We get y to be a function of u. It will be a to u f of t dt. That's exactly what we get. I'm taking out g of x and replace it by u. So I get a function of u. But actually u itself is a function of x, so y is a function of x. The question is, what is dy by dx? dy by dx will be dy by dx using the chain rule we have in calculus 1. dy by dx is dy by du. How to get dy by du? Now, y is a function of u, which is in the same form we have for fundamental theorem of calculus. Exactly the same form. So fundamental theorem of calculus part 1 says, if you need to evaluate the derivative with respect to u, that is nothing but f of u. But using the chain rule, you need to multiply by dy by dx, which is g prime of x. We need the final answer in terms of x. So what is the conclusion now? Y prime or dy by dx will be equal to what? It is f of g of x multiplied by g prime of x. That's exactly the formula we have here. So once you have a derivative of an integral function or a function defined in terms of integrals, a to a function of x f of t dt, so I can use the formula here that says the final answer will be just f of g of x times g prime of x. So that is more general form of the fundamental theorem of calculus part 1. Actually, we are combining the fundamental theorem of calculus part 1 together with the chain rule to get a new formula for such type of functions that are defined in terms of x. Okay, let us take a specific exercise and see how to calculate the derivative if we have such a shape. For example, example here says, find f prime of x where we have the following function. Let us say our function here, f of x, is the integral from 1 to sine of x. And here we have t squared plus 1, and that is dt. That's our function. This is a function of x for sure, because if you change x here, the value will be changing. Okay, what is the derivative? F prime of x. According to the formula we did now, you need to replace the sign here, replace t by the sign. So what do we get is sine squared, okay, t squared, sine squared of x plus 1, that is f of g of x, multiplied by g prime. So what is the derivative of the sine function? That is cosine of x. That's exactly the derivative of the function if we have function of x. Let's call this one part A, and let us do another part B here. If we have f of x is equal to another one here, what I will do, I will write x cubed downstairs here, and then I will write 2 upstairs like this. And then I have e to the power t, okay, times t dt. Okay, we have very nice function here, continuous, differentiable, everything we like about it. And we are interested to find the derivative of this function. Now, we have the function is appearing downstairs. So what should we do as before? We need to rewrite the function by using the properties of integrals. It will be minus integral from 2 to x cubed, and that is t e to the power t dt. Okay? Then we apply the fundamental theorem of calculus together with the chain rule to get the derivative of the function, f prime of x. Now, this shape implies now using the formula we derived here, it is simply you are replacing t by the function of x here, so that will give you x cubed. e to the power x cubed multiplied by, I'm replacing and multiplying by the derivative of this. The derivative of this is 3x squared. Don't forget the minus sign we have outside, and then simplify to get the final answer. Okay, so what will be the final answer now? This will be equal to minus, of course I have the number is 3 here, I will write it at the beginning, x squared, x cubed, that will give me x to the power 5, and then I have e to the power x cubed. That is a direct application for the fundamental theorem of calculus part 1 combined with the properties of integral and the chain rule. So these examples will give some ideas in how to use fundamental theorem of calculus part 1. Now I will write the most general form of this. I am combining 3 things here. The fundamental theorem of calculus part 1, the chain rule, properties of integral. To get the most general form of the fundamental theorem of calculus part 1. That would be the following result we have here. I'm keeping the theorem in front of us so that we can see things. So the last one, you can also write it as a conclusion of the fundamental theorem of calculus, or as a result of the fundamental theorem of calculus. What is that? If we have an exercise that says find f prime of x, where we have the following, okay? We have our f of x is defined this way. It will be the integral from g1 of x, okay? And we have here g2 of x. If we just give a notation here, for example, h of t dt, or whatever it is, we may rename this to be f, and we call this one y, and so on. It's just a notation. H of t dt. H is a continuous function. Everything is fine here. What is f prime of x? We can show that this f prime of x will be equal to what? It will be h of g2 of x multiplied by g2 prime of x minus h of g1 of x. I'm replacing now the lower limit here, multiplied by g1 prime of x. This is g1 of x. How to show this? How to show this? Find f prime. This is what we need to find at the end. We need to show this actually. How to show this? For how to get this result? This is the question. The idea is so simple. What you need to do, this is the solution of the problem. So this is the conclusion actually. We need to justify it. So how to get the answer here? I'm just writing it here so that you can use it later if we have, any exercise about fundamental theorem of calculus in the most general form. How to do this? Usually we need to use the basic things we have. The basic things we have is this, a to x f of t dt. So I need to reform this. So what I will do, using the properties of integral, I can write this one as g1 of x up to a certain number, call it a, whatever it is, h of t dt, okay? Plus, I will write here from a to g2 of x, what? h of t dt. Then we are done with these 2 things. Using the chain rule, etc., we have the following. I will just reform them now. This is minus, and then I have here what? I will have a and g1 of x, h of t dt, plus the second one from a to g2 of x, that is h of t dt. But now we have a formula for this, we have a formula for this, which is exactly what we are writing here. Okay, so using this formula, what do you get? I will start with the second term here. That will give me h of g2 of x times g2 prime of x. Chain rule together with the fundamental theorem of calculus. Then minus h of g1 of x multiplied by g1 prime of x. So what is the conclusion? This is the result here. Whenever we have a function defined in terms of integrals, where we have a function of x here, a function of x here, okay, based on the continuity of h and the conditions we have in the fundamental theorem of calculus, assume everything is fine, then what is the derivative here? It is h of the upper limit multiplied by the upper derivative minus the substitution at the lower limit multiplied by the lower limit derivative, and this is the justification for our calculation. Now we discussed mainly the most general form of what we call fundamental theorem of calculus. I will give you one more exercise about this to see how to apply fundamental of calculus, the fundamental theorem of calculus, how to apply the fundamental theorem of calculus in the most general form. Okay. Now to conclude this discussion of part 1 of the theorem, let us try to solve these two exercises. Here we have f of x is defined in terms of integral, where we have the lower limit is a function of x, the upper limit is a function of x. So it is a direct application for the result here we derive from the fundamental theorem of calculus part 1. Now he said, what is f of 1, f of prime of 1? Okay, what is f of 1, f of prime of 1? Let us find first f prime of x, then we substitute. Now what is f prime of x? According to our discussion, this will give me tangent inverse. I replace t by x cubed, then I need to multiply the whole thing here by the derivative of x cubed, that is 3x squared, minus, now I need to substitute x squared here, that will give me tangent inverse of x squared, okay, and all of this multiplied by the derivative of x squared, that is 2x. That is the first point here. Now let us evaluate the function at 1 and the derivative at 1. F of 1 plus f of prime at 1 will be exactly equal to. F of 1 is the integral from, I'm replacing x by 1, so this will be 1, this will be 1, and that is tangent inverse of t dt, okay? Plus, now what is f prime of 1? I replace here x by 1. So what do you get here is 3 tangent inverse of 1 minus 2 tangent inverse of 1. That is actually tangent inverse of 1. Because I have 3 minus 2 tangent inverse of 1. 3 tangent inverse minus 2 tangent inverse of 1. That will give me tangent inverse of 1. Okay, fine. So this is what we have. This is tangent inverse of 1. Now, according to the properties we did for integral, this is equal to 0 for definite integral. If we are integrating from 1 to 1, that is 0. What about tangent inverse of 1? Tangent inverse of 1 is just pi over 4. So that is the answer for this specific exercise, where we used the most general form of fundamental theorem of calculus part 1. One more exercise, and that will conclude the discussion of this theorem, first part. It says if you have a function which is called g here is continuous. Okay, so the condition of the fundamental theorem of calculus is there. We have continuity here, so we need continuous functions. Okay. Of course, e to the power t over 2 is also continuous. The multiplication is continuous, so everything inside is continuous. Fine. And it satisfies the following here. Of course, this is a function of x. And this equation says that this function of x is equal to this function of x. What do you need to do here? We need to have some idea about the function g at 4. We need to recover the function g, in other words. So what should we do? This is another way to apply the fundamental theorem of calculus. So what should we do to recover the function? We will differentiate. We will operate the derivative here in both sides of the equation. So what do we have? I will differentiate the left-hand side. I will differentiate the right-hand side. We have f of x equal to g of x. Then clearly we have f prime of x supposed to be equal to what? G prime of x. In order to recover the function here, I will differentiate to remove the integral sign. So what do we have here? If I differentiate both sides with respect to x, what will happen here? I will substitute with the upper limit, so that will give me what? E to the power 2x over 2, that is e to the power x, g of 2x times the derivative of this, which is equal to what? Which is equal to 2. That is the application for fundamental theorem of calculus. I am differentiating, and the upper limit is 2x, so I substituted here, and then I multiplied by the derivative. That's the first point. What is the derivative here? This is product of two functions. So it is e to the x plus x e to the x. That is easily to be done by the product rule of differentiation. Okay. Now I need g of 2x equal to what? I need to solve for this. What is g of 2x? I need to divide by e to the x. I need to divide by 2. So simply, if you write the right-hand side as e to the x times 1 plus x, and then you divide by 2e to the x, you have e to the x will be cancelled out. So g of 2x will be equal to what? 1 plus x divided by 2. Now he said find g of 4. G of 4. So what is g of 4? I have 2x equal to 4. So our x here is equal to 2. So the final answer will be 1 plus 2 divided by 3. That is equal, divided by 2. That is 3 over 2. I repeat here that we are getting g of 2x. And we need to evaluate g of 4. So I need to see what is x. 4 is 2 by 2. 2 by 2, so x is equal to 2. I substitute here 2. 2 plus 1 is 3. Divided by 2, so the final answer is 3 over 2. That is what we call fundamental theorem of calculus part 1. What is the second part of the theorem? Fundamental theorem of calculus part 2 says what? Okay, that is our next point. Now let us see the second part of the fundamental theorem of calculus. We still remember that if we need to calculate a definite integral for a specific function, we need to pass through what we call the Riemann definition. That is, we need to take the limit as n goes to infinity summation of f of x I delta x. And that is not always straightforward to be calculated. We saw some small exercises like integral of x squared or x cubes. It takes us time to find the final answer, which makes it difficult to apply this definition in order to find areas and volumes. Now, the fundamental theorem of calculus part 2 will help us to do the calculation. It says, if we have a continuous function on AB, and capital F here is any antiderivative of the small function, that is, the derivative of capital F is the small f on that interval AB, then if you need to calculate the integral from a to b, the definite integral from a to b f of x dx, it is simply is equal to the value of that antiderivative at b minus the value of that function at a. Find any antiderivative you like and calculate it at the end point minus the calculation at the first point or the evaluation at the first point. This is a big jump in calculus because it simplified the calculation part for definite integral. To get an idea about the second part of the fundamental theorem of calculus, I will remind you with something we have done in calculus 1 that says if we have two functions whose derivative are the same, f prime equal to g prime, then you know that f of x minus g of x always will be what? A constant. They differ by a constant. Two functions, they have the same derivative, then these two functions differ by a constant. Now, one point we have from part 1 of the theorem. He said here, you need to find any antiderivative of this small function f of x. But we know one of them now. We have, if we just have a to x f of t dt, this nice definition we did for a function called g of x. Now, I will ask you what is the derivative of this function here. If someone asks us what is the derivative of this, we know that g prime of x is nothing but what? F of x. So this function which is called g of x, which is defined in terms of integral, is actually an antiderivative for the small function f of x. Because once I differentiate, I get this. Okay, let me call this capital F. So, if you have any function which is antiderivative, then it's supposed to be g of x plus constant. Because we said if we have two functions, they have the same derivative, then they differ by constant. So, if you are looking for an antiderivative of f of x, you have one of them, which is this function. So to get all of them, you just add a constant, because any antiderivative is the same as this function, minus constant, or the difference between them is constant. F minus G is constant, as we said. Okay, fine. What we need to do here, if we calculated the right-hand side here, f of b minus f of a, f of b minus f of a, what do we get? If we calculate f of b minus f of a, that will give us the integral from a to b f of t dt plus constant c. I'm just replacing x by b. Minus, if I replace the x by a, I will get the integral from a to a, okay, f of t dt plus c, okay? When I subtract these two things, considering that this is equal to 0 by the properties of integral, and the c will cancel with the c, what do we get? We get the integral from a to b f of t dt is nothing but the evaluation f of b minus f of a. So simply how to find the value of definite integral. And the answer by this nice theorem says you just look for an antiderivative of the integrand, then evaluate it at the end point minus the evaluation at first point. That will be done in the following exercises we have here. For example, let us take a specific exercise here that says evaluate, for example, I have this, evaluate the definite integral from 1 to 3 e to the power x dx. Now, this nice theorem says you don't need to go and define the xi's, you don't need to find the summation stuff, you don't need to go and find the limit stuff. The only thing you need to do is the following. Go to the function inside and try to find an antiderivative of that function. Okay, if we consider the function we have here is e to the x. Now, if someone said, what is an antiderivative of this? What is capital F of x here? What is the function whose derivative is e to the x? So, a clear function is e to the x itself. The derivative of e to the x is e to the x. So, according to the fundamental theorem of calculus, 1 to 3 e to the x dx is nothing but f of 3 minus f of 1, capital F of 3 minus capital F at 1. That is equal to e cubed minus e. So you see we get the answer in one line here by figuring out what is the antiderivative here. Before, we were forced to do this through the definition, so we need to find the xi's limit. Sometimes we succeeded to reach the final answer, and sometimes we try to approximate only because we don't have formulas to evaluate the limit of a summation. Okay, so you see the beauty of the fundamental of calculus part 2. It simplified the calculation part for definite integral. We will see more exercise about this. In the following part here of the question here, it says, okay, it says evaluate the integral of, this is part B of the exercise here, says, let's call this one part A, and that's part B, that says evaluate the integral from 3 to 6, and we have here dx over x. Now let us imagine what we need to do. What's supposed to be done here if we are applying the definition? If we are applying the definition, then we need to find delta x, that is 6 minus 3 over n, which is 3 over n. Then we need to form the xi's that are a plus I delta x, and so on. Then we need to do this calculation 3 plus I delta x, that's 3I over n. Then we need to go through the limit case here, limit as n goes to infinity, summation I equal to 1 up to n, etc. f of xi 3 plus 3I over n times 3 over n. Then we have the function 1 over x. We need to substitute, simplify, take limits. So many things we need to do. The fundamental theorem of calculus says, come on, I will give you the answer in one line. How to do that? It says the only thing you need to do is the following here. Think about an antiderivative of 1 over x. And an antiderivative of 1 over x from our previous study we have is ln of absolute value of x. And then I will use this notation for the calculation here. Calculate this at 6 and at 3. Meaning, what is the meaning of this notation? If I said f of x and I wrote here ab, I mean by that f of b minus f of a. This is the notation will be used in calculus all the time for evaluating. So what should we do now? So using this notation we have here, and the fundamental theorem of calculus says you just evaluate at the endpoint the antiderivative here, which is the antiderivative of 1 over x. So that will give you ln of 6 minus ln of 3, which is simply equal to ln of 2. So now we feel the simplicity of these problems because of the fundamental theorem of calculus. Okay, so many examples we can do now by fundamental theorem of calculus part 2. The only thing we need to increase our skills or improve our skills in finding antiderivatives only. And that's basically what we will do in this calculus 2 or in the next material we have in calculus 2. We need to improve our skills in finding antiderivatives. Then finding definite integral will be simply evaluating at the endpoint minus evaluating of the first point. But we need to be very careful when we use fundamental theorem of calculus. We do not forget the conditions we have in the theorem. Let's read it again. It says if you have the function f is what? Continuous. This is the key that you need in order to apply the fundamental theorem of calculus part 2. Then you can have the conclusion here. So what happened if the function inside is not continuous or has like what we call infinite discontinuity? We need to wait up to what we call improper integral to solve the question. But let us see the following exercise and comment on that condition we have in the theorem. Now let us see this exercise here. That says what is wrong with the following calculation. I will start from the beginning to the end and we will see what is the wrong step here we do. I assume someone asked me to integrate this and then I said, come on, this is what we have here is just the integral of x to the power minus 2 from minus 1 to 3 dx, okay? So I will say, according to the fundamental theorem of calculus, what I need to do is just to find the antiderivative of this, which is the antiderivative of x to the power minus 2. So what do we have here? I will write x to the power minus 1 over minus 1, that is minus 1 over x squared. Once we differentiate this, we get 1 over x squared. That is an antiderivative of 1 over x squared. Then, according to the nice theorem we did, it says I need to evaluate this from minus 1 to 3. So what I will get here, I will take the minus sign common factor, then I will substitute by 3 to get 1 over 3, then minus, and we have a minus sign, so that will be plus 1, okay? So that's what we have exactly here. I'm substituting 3 to get 1 over 3, then a minus sign in the formula we have, and another minus come from minus 1, so that is plus 1. Then I will end up with minus 4 over 3, okay? And we'll stop here and I need to discuss now what is wrong or what is the wrongest step I did here. Is this one make sense or doesn't make sense first? I have the integrand is non-negative, always greater than 0, okay? And I'm integrating here. And we had one of the comparison properties for integral says if this is always non-negative on AB, you remember this, we have the integral from a to b of the integrand here, dx, supposed to be also greater than or equal to 0. But something amazing here. We are integrating non-negative quantity, and we end up with a negative quantity here, which is, it seems to be invalid here. It doesn't make sense, let us say. So what is wrong? What is wrong in the calculation here? I'm doing things correctly here. I'm integrating here, so I'm getting an antiderivative and then evaluate. We said, come on, we have a key which is lost. We used it. We cannot use something which is not there, okay? So what is that key? The continuity of the function is very important in the fundamental theorem of calculus. If you don't have continuity, you do not have the conclusion here. Let us check if we have continuity or not here. Let us check if this function is continuous between minus 1 and 3. Clearly 1 over x squared has a problem at x equal to 0. If you substitute x equal to 0, we have infinite discontinuity at that point. So what do we have here? This calculation, all of it is not true. Doesn't make sense. Why? Because once you move from this step to this step, what you are using here actually is fundamental theorem of calculus. And the question, do we have this? Can we use this one? And the answer, absolutely no. Why is that? Because the function we have is not continuous. So meaning, it does not satisfy the conditions we have in the theorem. If we lose this key, which is called continuity, especially if we are losing it in the infinite discontinuities, then we have problem, and this problem will be treated later. It's called improper integral. Okay, then we discuss this one through limit cases and etc. For the time being, if the integrand is not continuous over the whole interval, I cannot use what we call fundamental theorem of calculus. Rather, I will use something called improper integral, the definition of improper integral. So this concludes the discussion of fundamental theorem of calculus. Yes, we have two parts. Part one that talks about the derivative of the integral, and the second part is talking about evaluating definite integral that says simply you need to find an antiderivative, evaluate at the endpoint, minus the evaluation of the antiderivative at the lower limit, which is called a. That is the end of fundamental theorem of calculus.